Hi everyone and welcome to my presentation of our L2RPN with Trust submission for ICAPS 2021. My name is Matthias Dorfer and today I'm representing EnliteAI's reinforcement learning team, which you can also find under the name MazeRL on the leaderboard. In my talk I will show how to approach power grid topology planning with model-based reinforcement learning. So just a quick intro. At EnliteAI, we are basically 6 people working on reinforcement learning. All of us were at some point a little bit involved in our challenge contribution, but the rest of our time, besides working on projects, we are also, for example, developing the applied reinforcement learning framework MazeRL. All right, let's get to the central idea of our submission. So after we started playing around with the grid to op env a little bit and looking at previous submissions, we came up with a few design principles that we tried to impose on ourselves. So the first one was we wanted to find a solution that preserves the original action space without pre-computing, for example, fixed limited sets of action candidates. Because this might potentially introduce some bias or even limit the optimal solution. Then the second one is that we wanted to keep grid-specific or dataset-specific engineering as low as possible. This turns out to hand-engineered rules that only apply, for example, to the ICAPS 2021 dataset. And last but not least, we wanted to make sure to work with a methodology that first of all scales well to larger topologies, is somehow a nice fit or natural fit to AI-powered control room assistance tools, and especially also supports long-term or scenario planning. In terms of compute budget that we had available, this was at max 4 compute nodes, each with 64 cores, and we were training with a single GPU. Except for the restricted compute budget here for reinforcement learning, the upper design principles really work well or fit really well to the AlphaZero algorithm. And now the central idea of our submission is that we extended the RL algorithm AlphaZero to make it applicable to the topology planning problem in large power grids. So let's just see which steps are required for developing and training such an agent. So I will start with the model training workflow. This is quite general, so we always have in the center of such an algorithm a distributed MCTS sampling, which runs in parallel and produces an asynchronous stream of MCTS sampled grid trajectories. These trajectories are fed into a rolling trajectory buffer. And once we have enough transitions sampled here, we can feed these into our policy and value network optimization stage. So we train our policy and value networks, and after every epoch, whenever a new set of weights is available, we write the latest version of these models back to the MCTS sampling stage, and the whole process starts from scratch. So this is now the training workflow. In terms of agent interaction workflow, we also took a small modification. So we have here our agent, we have here our MazeEnv, which basically wraps the grid to op environment and adds a few nice features on top. Produces an observation, and then the agent can pick a topology action. For the specific problem, we now intercept this classic agent env interaction loop with a critical state observation and skipping wrapper. So what's going on here is that we observe if the current state of the env is critical. If it's not, we simply run a loop just executing the no-op action. But if we really encounter a critical state that requires an action, we now really query the agent to to predict actual topology change action. Yeah, and that's already it. Speaking of the topology change action, so this is probably the most important bit of our approach. So what we did here is we took the Bernoulli distributed multi-binary action space of the grid to op env, which is related to the bus switching problem, and converted it into a substep action space that introduces intermediate substeps on top of this actual env step that now allows us to take multiple discrete actions at a time. The intuition for this one is, because it's not really time to present the details here, the intuition is that this is somehow a hierarchical autoregressive action selection. And this doesn't require explicit action space reduction, because due to the hierarchical decomposition of the actions, we can apply extensive masking in the lower layers of this selection process, and yeah, this becomes quite efficient, and we can preserve the original action space here. In terms of reward formulation, nothing fancy was used. It's basically just the exponential decay of the weighted sum of the maximum load on any power line and the number or count of currently offline power lines. All right, now to the heart of the method, the MCTS policy. We also took here a few modifications. In general, let's say we have a critical state encountered, then we can sample our actions and build up the MCTS tree. So the first modification, and this is due to the limited compute budget, is that we developed a heuristic value function and don't learn the value function from scratch. An additional change is also related to compute budget, and this is early stopping of the MCTS search process. So once a critical state is recovered or found, we build up the tree, and as soon as a recovery state is found, we just early stop the MCTS search process here. And yeah, the third point in here is also related to this, because once recovery states are found, we don't select the action up here by visitation count or value, but we bias the action selection towards these recovery states. Okay, so the last bit that is now missing are the features and the networks that we employ. So we started out with quite complex graph convolutional models, but in the end we were using quite simple features and models. So these features comprise, for example, line status, loads, current flow, deltas between substations of these features, and so on and so forth. A bit more interesting, we of course use observation normalization to make sure the models learn efficiently, and we also use observation stacking to also have some dynamics of the env represented in our observation. Yes, and all of this is then processed with a simple late fusion style feed-forward model, first processing the individual features, concatenating them, and then feeding into the policy and value networks. Okay, let's just assume these models are trained and we can get to the deployment stage with quite little compute budget actually. So how can we deploy such an AlphaZero model? So on the lower end of the spectrum, we could simply apply argmax policy. On the other extreme, this is what we would like to do, of course, is full MCTS sampling. With a single core on the submission server, this of course is not possible, which is why we opted for a compromise that still works sufficiently well, and this is a form of beam search that we employ. So how does this look like? So we encounter a critical state, and then we take the most probable action. Maybe this already resolves the critical state. At some stages or situations, it might be also required to take multiple actions to really get out of this critical situation, but it can still be the sequence of most probable actions. However, if this is not the case and the sequence of most probable actions, for example, leads to a diverging power flow, we scale up. We call this survival mode and dynamic computation budget. We basically scale up and just explore different branches in this search tree. And yeah, hopefully a few of these trajectories will really recover from the critical state. And yeah, we can preserve the grid in a stable and running state. As we now already have this kind of methodology, we can also reuse it for raising alarms and getting human attention. So we have these multi-step horizon rollouts, and whenever we encounter a critical state that might lead to a diverging power flow or blackout with a high probability, then we inform the human operator about upcoming critical situations by raising an alarm. Yes, and this is pretty much our approach in a nutshell. Thanks a lot for your attention, and yeah, hopefully see you in the next edition of the challenge.